Today I want to explain boilers, hardness of water, various treatments of water in industrial chemistry, and which was introduced in Dr. V.S. Krishna Government PG Autonomous College. Now I am dealing the first topic, boilers. In this boilers I want to discuss about the definition of a boiler, principle and uses of boilers and classification of boilers and working of some boilers I want to explain. Now see the definition of the boiler. Boiler is nothing but a steam generator in a closed vessel in which water is there. That water is converted into steam by applying the heating, by giving the heat, and it is an example of heat exchanger. Heat exchanger means the steam have produced here. How the steam is produced is that when we apply the heat to the water converted into steam after its boiling point. Water takes energy from the heating by fuels and it gets energized, and its kinetic energy also increases. Here the boilers is used in the industries. The industries large type of boilers are there. In houses also we are using the boilers, but it is a small purposes like household purposes like milk boilers or pressure cooker like that. But in industries large type of boilers are used to produce a more steam. And now see the principle of a boiler. Boiler is a cylindrical vessel in which water is present, and above that water steam should be produced, so that there should be a space for the steam in that vessel. And mostly water is used in the boiler, or alternative fluids are also used, but here alternative fuel is not used that much. Water is heated by giving a heat and it produces steam, and that steam is passed through the different pipes, various pipes for generation of the power or other. It means to convert the steam energy into mechanical energy. Next, see what are the basic parts of the boiler. Basic parts of the boilers. The boiler have cylindrical shell, furnace, feed water, that is a water inlet, feed water in the sense water inlet, steam outlet and steam space and heating surface, and some accessories are there. Accessories like water level indicator, pressure gauge, like that. If you see the figure you can understand. Here the horizontal axis, it is a cylindrical shell in that water is feeded, and water is feeded with the inlet pipe, and that water is passed to the different pipes of smaller pipes, and some it requires different pipes and sometimes it not requires the different pipes. Under that flame is there, and flame takes the that flame energy taken by the water and it converted into steam after its boiling point. The produced steam is come out and it is on the water, Next, see the uses of boilers. Boilers are used in various industries such as power generation, textile industries, hospitals, food industries, pharmaceutical industries and chemical industries, and boilers are used. Not only this, long travelling ships. In long travelling ships, high density fuels are used as a like how we are using the diesel or petrol in vehicles. In that ships they are using the high density fuels. The high density fuels are very thicker. The thicker cannot be useful for the machinery purposes, that is for converting to the mechanical energy it is not useful, so that should make it into a less thicker. For that they are using the steam. That steam pipes are passed through that fuel. It means the steam is passed around that fuel is there, that takes the energy from the steam and it becomes less thicker, then only it is useful for the ships. So in this way long travelling ships are used the boilers. Not only that, power generation, for power generation and heating purpose are also used boilers. And see the basic parts of a classification. Classification of a boilers. In this classification depends on the design, depends on the specifications. Boilers have many types. There is a location of a boiler shell axis, flow medium inside the tubes, and boiler pressure. Depends on the methods of water circulation, depends on the types of fuels used, and depends on the number of tubes. And in this way the boilers are classified. Again, these are classified into many ways, and see one by one. First one is the location of a boiler shell axis. The boilers may be different types. Horizontal boilers are there and vertical boilers are there. Sometimes inclined boilers are also used. Horizontal boilers, like example Babcock and Wilcox, and Babcock and Wilcox boilers are used in the ships. And vertical boilers are example for the Cochrane boiler, locomotive boilers, like that. And next classification, if you see the flow medium inside the tube. For this examples, Cochrane and locomotive boilers is for fire tube, and Babcock and Wilcox boiler is for the water tube. Here the fire is passed through the pipes, or fire or hot gases are passed through the pipes, around that water is present. For that the examples are Cochrane boiler and locomotive boiler. And next, if you see the water tube boiler, water is in the tube and above that or below that flames are there. So, for this the example is Babcock and Wilcox boilers. Next, depends on the pressure also, the boilers are explained in different way. Some produces a low pressure boilers, some produces a high pressure, and low pressure boilers is less than 80 bar. For that the examples are Cochrane and locomotive boilers, which produces a very low pressure, whereas high pressure producing boilers are Babcock and Wilcox and Benson boilers. And next, methods of water circulation. Depends on the methods of water circulation. These are classified into two ways. One is a natural circulation and another one is forced circulation. And natural circulation, it produces a less pressurized steam in boilers, whereas in forced circulations it produces high pressure boilers, high pressure steam in the boilers. For that the example is Benson boiler. And another classification is types of fuels used. Here the fuels may be the solid fuels or liquid fuels, gaseous fuels. Gaseous fuels like industries producing waste gases that have very hot, the gases of, coming from the industries are very hot. That gases are also used for the boilers for producing steam. And electrical energy is also used for boilers, and nuclear fuels are also used. And another classification is based on the number of tubes. Sometimes we are using the single tube, sometimes multi tubes boilers are used, multi tubes are used. And another one, boilers mobility. Boilers mobility, if you see the boilers mobility, some are stationary, some are mobile. Stationary boilers used in the power plants, and mobile boilers is used in the marine boilers. Babcock and Wilcox boiler, that one is used in the long travelling ships. And see some working of water tube boilers. Here water tube boilers is that it consists mainly two drums, one is upper drum and another one is lower drum, as shown in the figure. And lower drum, it is almost all one drum, but downward water is present, above that steam is present. So, that one, the steam present in the above one is called the upper drum, and below that water is present, the water we are calling as mud drum. And here with the flame we are heating the water. Here this is the inlet, one side is the inlet, water is passed, and here the water is passed through the various multiple tubes. Here this one is a multi-tube one, and whenever we are heating with the flame, that water gets energized and it converted into steam after its boiling point, and steam have less weight, so that it will come out from the water and it reaches at the top of the water level, and more steam is generated. That steam, as when pressure is more, that should be taken to outlet, that should be removed from that space, removed from that area, so that steam outlet is there. Next, another one, 5 tube boiler. Here the red one is in the figure. Here the fire is passed, so or hot gases are passed through the pipes, around that water is present. So whenever the water is there, the water takes the energy from the fire, and then that water converts into steam after its boiling point, like that, and flue gases will come out, and another design is there at the end of the flue, and at the end of the gases, at the end of the hot gases. So this is the 5 tube boiler. And next, if you see the comparison between the water tube and water tube and 5 tube boiler. See here, in 5 tube boiler only hot flue gases pass through the tubes and water surrounds them, whereas in water tube boiler, water passes through the tubes and hot flue gases surrounds them. And if you see the working pressure of the 5 tube boiler, the working pressure of the 5 tube boiler is very low, that is 20 bar only, whereas working pressure is high in water tube boiler. And here the rate of steam generation and the quality of the steam is very low in case of a 5 tube boiler, whereas in water tube boiler the rate of steam generation and quality of a steam is more in case of water tube boiler. And here the load fluctuations can be handled in the 5 tube boiler, whereas load fluctuation cannot be handled in 5 tube boiler. But in water tube boiler, load fluctuations can be easily handled. And here for 5 tube boilers it requires more floor area, whereas for water tube boilers it requires less floor area. And if you see some more differences, and 5 tube boiler is difficult to transport, whereas water tube boiler it is very lightweight and transportation is very easy. And here in 5 tube boiler only 75% up to 75% efficiency is there, but in case of a water tube boiler it have more efficiency, that is 90% efficiency is there. And water here in 5 tube boiler, water does not circulate in a definite directions, whereas in water tube boiler water circulate in definite directions. And the drum size is used in the 5 tube boiler is large and damages may be occur, and whereas if any damages occur in the water tube boilers, that can be regretted, that can be easily replaced and easily repaired. So these are the differences between the 5 tube and water tube boilers. And here some more boilers are there: locomotive boilers, Benson boilers, and Wilcock and Boycock boilers. And like that so many of boilers are there. If you see the locomotive boilers, that locomotive boilers is used in, it is a vertical boiler or Cochrane boiler which is used in railway engines, but now it is not used. Previously it is used. Why? Because it is having more manpower and Why it is not used now? Because it is having more manpower in those days, and not only that, it is difficult to carry those boilers, and the smoke produced in that boilers is more. Because of that, locomotive engines, locomotive boilers are nowadays it is not available, and it is not used in railways. And some more, if you see the boilers, Cochrane boiler, this is the figure of the Cochrane boiler, and Cochrane boiler, in that steam is produced from the top, and here water is there. Here hot gases are passes through the tubes, around that water is there. That water produces steam, and above that the steam will produce. Here so many of accessories are used, water level indicator, and how much of water is required. If more water is fed, there is no space for the steam. So, water level indicator is also required, and if water is converted, all the water is converted into the steam, then there is no water, then also it is difficult. So, difficult to produce a steam. So, water level indicator should be there, and some pressure gauge is also required. Pressure gauge, to how much of a pressure is there, from that steam is more, if steam is more, pressure is more. So, to release that pressure, so pressure gas is required. Like that, some accessories are also used in these boilers. Next, if you see another one is a Babcock and Wilcox boiler. This is a multi-tube boiler, already we have seen in the water tube boilers. This is a water tube boiler. Water is passed through the multi-tubes. Here the 4 tubes are there, 1, 2, 3, 4, 5 tubes are there. Through that water is passed. The near to the water, flame is there. That flame taken by the water, and it converts into steam, and it is a horizontal one, horizontal boiler. This is a horizontal boiler and multi-tube boiler. So, like this we can use boilers. Boilers have many uses in power plants and in drug industries, and boilers, especially boiler water, it should be soft water. Next topic is hardness of water. In this hardness of water, definition and types of hardness and units and determination of hardness and levels of hardness we will discuss. Now see the hardness of water. So, water, without water we cannot live. Water has many uses, and in living, for living beings, for industrial purpose and textile, and so many uses are there. And if you see the hard water, it contains chloride, carbonate, bicarbonate, sulfates of calcium, magnesium and heavy ions. Hardness of water is a property of water, and it does not produce lather with soap. And soft water, and now see soft water. Soft water, it is free from chloride, carbonate, bicarbonate, sulfates of calcium and magnesium and heavy ions. So, now you learn that what is the hard water, what is hardness water, you learn, and here the hardness water again divided into two types. One is the temporary hardness and another one permanent hardness. These two are based on the anion present in that. Anions like carbonate, bicarbonate, sulfate, chloride. Based on these ions, these are classified into two ways. One is temporary and second one is the permanent. Now see the temporary hardness. Temporary hardness, it is a type of hard water and it contains carbonate, bicarbonate of ions, carbonate and bicarbonate ions of calcium, magnesium, and heavy ions are also there, and this can be removed by easily just by heating, or with the addition of the lime also we can remove this hardness. And if you see the permanent hardness, and this cannot be removed easily, and this is due to the presence of sulfates, chloride of calcium, magnesium and heavy ions in the water, and these are not precipitated when we supply the heat or a temperature. So, this can be removed by using a water softening methods. So, water softening methods like ion exchange method, reverse osmosis method. So, from that only we can remove the permanent hardness. We cannot remove permanent hardness by simple heating. Next, see the units of hardness. So, hardness are so many of units, but mostly used units are ppm, milligram per liter. ppm is parts per million. Parts per million is that it is 10 power 6 parts of a water contains how many of calcium carbonate equivalents are present. Suppose one part is the present, then it is called 1 ppm. If two parts are there in the 10 power 6 parts of a water, it is called 2 ppm. So, 1 ppm equal to 1 part of calcium carbonate equivalents hardness in 10 power 6 parts of water. And the same way the other unit mostly used one is milligrams per liter, milligrams of calcium carbonate equivalents present in 1 liter of water. So, 1 milligram per liter is equal to the 1 milligram of a calcium carbonate equivalent hardness of 1 liter of water. So, these two units are equal, we can use the ppm or milligram per liter. So, milligram per liter equal to 1 ppm. And now see the determination of hardness. In this determination of hardness, we have 3 parts, and another one, this can be determined by using titration method. The titration methods are, we have so many like acid base titrations, redox titrations, complexometric titrations, precipitation titrations. But here we are using complexometric titration for the determination of hardness. For determination of hardness we have 3 parts. First one is the preparation of a standard solution. The standard solutions may be zinc sulfate or any other like calcium salts or magnesium salts we can use, and second part is the standardization of EDTA, and the third part is determination of total hardness by given sample. Given sample is from the house or outside the areas, we can take the water from that, in that how much of hardness is present we can determine. So, in this we are using some solutions, and here zinc sulfate solution we are using, EDTA solutions we are using, and another one indicator is required for color change, for reaction completion. We have to know the reaction completion. For that we are using indicator. The indicator is here EBT. EBT is called aerochromo-black tea. The structure of that one is here on the slide, and here it is a solid one. That solid one we can make it into a solution, and that solution, looking that it is a very thick blue. and indicator is used for the color change, and another one buffer solution. Buffer solution is here we are using basic buffer. The basic buffer prepared from ammonium chloride and concentrated ammonia. And next see the preparation of a first part of this one of the determination is preparation of standard zinc sulphate solution. Just we are weighing the amount of zinc sulphate solution, zinc sulphate substance, suppose 0.01 molar, 0.01 molar. If you want to prepare the weight of a zinc sulphate, we know that 287. From the 2.87 grams of zinc sulphate is weighed and transferred through the funnel into the volumetric flask. That volumetric flask. Here we are taking the 1 liter volumetric flask. Whenever we are transferred, and after that we are pouring the water, and up to the mark we are make it into solution, and then we are getting the zinc sulphate solutions. We are prepared the standard zinc sulphate solution. That standard zinc sulphate solution of known molarity, that molarity of a zinc sulphate solution is 0.01 molar. Next part, this is the first part, and the next part is the standardization of EDTA. So, EDTA we have to standardize. Why? Because we do not know the concentration of the EDTA. For that we are using the zinc sulphate solution. Using the zinc sulphate solution, for the zinc sulphate solution concentration is known, and using the zinc sulphate solution we are finding the EDTA molarity. So, for this, in burette we are taking the EDTA solution, in pipette standard zinc sulphate solution is we are taking, and that zinc sulphate solution is transferred into the conical flask, and that conical flask we are adding the buffer 10 ml, and EBT 1 or 2 drops of EBT is added. EBT or areochroma black tea or a dye, sometimes we are calling as a dye, that dye is here EBT. And here the buffer we are added here is because of to maintain pH, because to maintain the pH, here the pH is 829, so in that only the reaction is stable. Here the indicator we are using, indicator is here EBT, and buffer solution is ammonium chloride ammonia. And while doing the titration, just then what we have to do, in burette we are taking EDTA, and in conical flask we are taking some solutions, those are zinc sulphate, buffer, indicator. So, whenever we are adding the indicator to the zinc sulphate solution, we will get the wine red color. So, the final reading, if the reaction is completed while we titrating with the EDTA, the reaction is completed if it changes from wine red to blue. Blue is like a indicator color. So, from that we can calculate the molarity of EDTA. So, EDTA molarity we are calculated. After this, using the EDTA molarity we can calculate the hardness of water. So, here the color changes, you can observe wine red to blue. So, that one is the metal EDTA complex. Actually, the metal EDTA complex does not give any color. Because of indicator only we are getting the colors. So, this is the principle involved in that. Zinc dye is EBT, zinc EBT color is wine red color. Whenever we are titrating EDTA, only parts of the EBT is reacted with the zinc. The remaining parts are zinc is in the solution only, that zinc is reacted with the EDTA. At last, whenever the zinc ions are completed in the conical flask, at last the Zn2 plus complex is dissociates, the dye color will come out, the dye color is a blue color. This is the principle involved in the hardness of principle involved in the titration. Next, see the third part, determination of a total hardness of a given sample. In the same way, how we are doing the EDTA titration, in the same EDTA with the zinc sulphate, in the same way here we are doing, but instead of a zinc sulphate solution, here we are taking the sample of water. Sample of water, we are collecting the samples of water from various regions that contains ions, calcium, magnesium and heavy ions. So, in terms of a calcium carbonate, we are finding the hardness. So, same way in burette EDTA we are taking, in conical flask 100 ml of sample solution, sample for water is taken, and to that buffer solution is added, EBT indicator is added. So, here the same principle, only the part of the ions are complexed with the EBT, the remaining parts are in the solution, the remaining only part of the calcium magnesium ions are complexed with the EBT, the remaining are in the solution only. So, whenever the titration is completed, I mean all the calcium and magnesium ions are complexed with the EDTA, then at last there is a release of EDTA, the release of EBT indicator. That EBT indicator color is blue color. So, you can observe that the color changes from wine red to blue, and like this we can calculate the molarity of water in terms of calcium carbonate. In terms of a calcium carbonate, for 100 ml we will get the 0.022 grams, and then if we convert these grams into ppm, we will get a 220 ppm. Next, if we see the units, ppm is used and another one milligrams per liter. And one more thing we have to know, that levels of hardness. Here the 220 came in the experiment, which water is useful in the industries and which water is useful for the drinking purpose, then that can be detected by using this method. So, here the levels of water, if you see the levels of water here below 60 milligrams per liter or 60 ppm is considered as a soft water, that is good for drinking, and industrial purpose also it is good. And in boilers soft water is used, otherwise the scales will form. If to remove the scales is difficult, not only that, production of a steam will be less, so that soft water is used in the boilers. So, and if it is in between the 60 to 120 milligrams, it is moderately hot, and if it is at 120 to 180 milligrams, it is a hard water. If more than 180 milligrams per liter is there, it is too hard, it very hard, it is not useful for the boilers or not useful for the drinking purpose. So, depends on this, I can conclude this, soft water or hard water we can find by using the determination of hard water. So, that water is useful for boilers or drug industries. In many of the drug industries or medicinal purposes, we are using the soft water only. Next topic is various treatments of water. In various treatments of water, we have so many of water treatments are there. Those are primary water treatments, secondary water treatments, tertiary water treatments, but most effectively we can remove the hardness by using a water softening methods is a tertiary water treatment methods. Tertiary water treatment methods are distillation method, evaporation method, oxidation method, ion exchange method, reverse osmosis method, crystallization method, solvent extraction method, precipitation method, micro and ultrafiltration method, adsorption and electrodialysis. Like that we have many of tertiary water treatments, and in that I want to explain only two processes. Those are ion exchange method and reverse osmosis method. So, first see the ion exchange method, after that we will see reverse osmosis method. In ion exchange method, here the resins are used. Resins are two types of resins are there. Those are cation exchange resins, anion exchange resins. And how the water, pure water is produced, just removing the anions and cations, how the process is, and we will explain next. And next, degeneration of the resins. If resin is completely exhausted, and how we have to regenerate the resin. All this will explained in the ion exchange resin. First see what is a resin. A resin is looking like a small granules, like if you observe that it is like a mustard seeds, like a small round mustard seeds, like that it is looking. See the figure is also there in the slide. It is which is insoluble in water, and it have cross-linked long chain organic polymers, and they have small pores in that, pores in structure, and in that pores the cations or anions will exchange, and they have different functional groups attached to that. But the different functional groups, in the sense, if it is a cation exchange resin, one type of a functional groups are attached, and if it is an anion exchange resin, another type of groups are present. So, depends on the anion exchanging properties and cation exchanging properties, the functional groups are replaced. Functional groups replaced and the functional groups are changed. Then the resins are also differed. See the first one, cation exchange resin. What is a cation exchange resin? Both we are using, cation exchange resin we are using in this water treatment, anion exchange resin is we are using in this. So, now see what is a cation exchange resin. Cation exchange resin, it contains acidic functional groups. It means H plus ions. In water, H plus and OH minus is there, or here the H plus ion should be removed from that from the resin. So, cation should contain the H plus ion. So, that type of a groups should be present in the cation exchange resin. The cation exchange resin containing COOH groups, SO3H groups, like that. You see the cation exchange resins examples. Here the SO3H group is there in that figure. H plus is removed, and calcium and magnesium ions are exchanged with that H plus ions. It means in that pores H plus ions is exchanged with the calcium and magnesium ions of the hard water, and this is a cation exchange resin. And next we will see the anion exchange resin. Anion exchange resin consists of a basic functional groups like quaternary ammonium groups, and these are these exchanges here. Suppose OH minus is ion is present in that OH minus ion will exchanges the chloride, sulphate, carbonate, bicarbonate ions. So, from that we will get the OH minus outside, and these groups in the sense hardness causing anions like a chloride, sulphate, that groups are go into the porous structure of resin. This is the example of anion exchange resin. And now see the process of how to remove the calcium, magnesium ions and chloride, sulphate ions. That is hardness causing ions, how we have to remove, we will see in the figure. Here two drums are there. So, two drums. In the first drum, that is in first step, in first step hard water is passed to that drum that contains a cation exchange resin. that cation exchange region is a bed. Whenever the hard water is passed through the cation exchange region, the cation having here the H plus ion replaced, and the hard water containing calcium, magnesium is sit in that cationic bed. So, H plus ion, more H plus ions will come out from that drum, that means it is having more acidic character. That water is passed through the anion exchange region. That anion exchange region, some more ions in the hard water like chloride, sulphate, that ions are exchanged with the OH minus of the anion exchange region. That OH minus is come out and the H plus ions are already come out from the cation exchange region. These two are combined and give water, that is soft water is coming from that. So, this is the process of ion exchange region, and in this we are getting the soft water. And see here it is in the industry, we went to the IDPL industry. In that ion exchange region had the two regions are there, one is a cation exchange region, is another one is anion exchange region, and this is used in the drug industry, preparation of the drugs. See here H plus and OH minus of the anion and cationic bed is removed, then all the cations of calcium, magnesium and anions like chloride and bromide, not bromide, chloride, sulphate ions are on the bed, on the cation and anion beds. Then there is no more removal of H plus and OH minus ions, then that type of regime we are called as exhausted regime. That exhausted regime is again we can regenerate. How we have to regenerate the exhausted regime? Just simply by pouring that reagents in the concentrated HCl, cation regime will exchanges the cations. Just we are pouring the cation bed in the concentrated HCl, then H plus ions will taken by the regime and all the ions, hardness causing ions will come out. In that way we can regenerate the cation exchange regime, and similar way cation exchange regime also we can regenerate it by using a sodium hydroxide, concentrated sodium hydroxide. By using that, depending on the three properties, these ions will exchange. The three properties are, one is a concentration and another one is a size of the cation or size of the anion and sizes, and the one is the concentration and size of the ion and the pore size. And next see the topic of reverse osmosis. This reverse osmosis also for removal of hard water, hardness causing ions, removal of hardness causing ions. In this we can use a semi permeable membrane, and what is, before going to that reverse osmosis you have to know what is osmosis. After that we will learn the reverse osmosis. Now see the semi permeable membrane. In reverse osmosis we use the semi permeable membrane. What is a semi permeable membrane is that it is a biological or a synthetic polymers, polymeric membranes, and synthetic membranes like a polymeric membranes, and these membranes allows only one type of molecules. Suppose for example, biological semi permeable example as lipid layers or cell structures. All cell also have the semi permeable membranes, and best example is a egg shell containing, under the egg shell we have a thin film layer. The thin film membrane is also acts as a semi permeable membrane, and synthetic permeable membranes are polyamide membrane. These are used for water purification. And see the osmosis. What is osmosis? Suppose in osmosis solvent, suppose pure water, that solvent is a pure water, and solution like sea water. If you take sea water in earth, on the earth so much of sea water is available. From that sea water we can prepare only the from that sea water we can prepare pure water. That is reverse osmosis, but in osmosis what will happen we will see. So, here one side solvent is used and another side solution like a sea water we are using, and these two are separated with the semi permeable membrane. Whenever separated with the semi permeable membrane, here the solvent particles move through the semi permeable membrane and this solution level is increases. So, this is the osmosis, this is osmosis. Why it is passed? The solvent particles only pass the semi permeable membrane is that because of osmotic pressure. Here the solvent have more osmotic pressure, due to of that pressure it moves towards this. And if we reverse that, what will happen? If the applying the pressure in reverse osmosis, what we are doing that we are applying the pressure on the solution like a sea water. Sea water contains so many of minerals, calcium, magnesium and chlorides, so many of minerals are there. That sea water, on that sea water we are applying the pressure, that pressure should be more than this solvent having osmotic pressure, more than the solvent osmotic pressure. So, if we applying a more pressure on the solution, then what will happen that the solvent particles of the solution, the solvent of the solution will move through the semi permeable membrane and the solvent level increases. So, pure solvent is taking out from the semi permeable membrane in reverse way. So, this is the reverse osmosis. Hydrostatic pressure is applied on the solution on one side, the solvent flow is reversed here, that is solvent is forced to move from the solution side to solvent side through the semi permeable membrane. This is observed in the reverse osmosis. So, in this reverse osmosis method, pure solvent is separated from the contaminants rather than removing the contaminants from the water, and this is called superfiltration or hyperfiltration. And this reverse osmosis method and ion exchange methods are useful in many industries. Not only the industries, for drinking purpose also we are using this reverse osmosis methods and ion exchange methods in small scale, but in larger scale it is used in the industries like a drug preparation, and not only that, boilers also should contain only soft water. For preparing the soft water from the hard water we are using these methods. Thank you.